Okay, now we'll talk about the more traditional and systematic way to obtain a model using Newtonian mechanics, and it's based on what is called the one-body diagram. So, as the name suggests, you have to make a representation of this one body, and you add the forces pointing in the direction they act on the body. You also put the moments, and usually you use curve arrows, and also they are indicating the way in which the torques are, or moments are, acting on the body. Of course, you need a reference frame, a coordinate system, and then usually you indicate the degrees of freedom associated with the body in translation and in rotation. So the methodology that is used in this systematic way of dealing with mechanics and this Newtonian approach is to sketch what is called the free body diagram. It's a one body diagram with all the bodies that are in your mechanical problem, and for each of these one body diagrams you put the degree of freedom in rotation and in translation, and you write down Newton's second law in translation and in rotation. Then you apply the constraints. You will see, as we've discussed previously, that there are links between the different variables, links between the different equations, and these you'll have to eliminate. And when you do that, you come up with a certain number of differential equations that are describing your mechanical system, and we'll apply this on the cart and pendulum system. Okay, so here's this example that will be modeling using this Newtonian approach. Later on in the course we'll also model it using the Lagrangian approach. So you have a pendulum hanging on a cart. So the cart has 1 degree of freedom. It can travel on a rail, and the degree of freedom, as you can see, is x. There is a force acting on this cart. It has a certain mass, and there is a friction force, right? Below the cart you have this pendulum. It's a rod of a certain length. It has a certain mass, and then you have this end mass. So the whole system, right, has a certain center of mass, which is here, and it's here that gravity is acting. Okay, and there is also a frictional torque, which is this one. Okay, so in this very systematic approach, well, what you do is to take the two one-body diagrams, and here you have two bodies of interest. You have, of course, the cart, which is body 1, and then the pendulum, which is body 2. Just it's the same drawing, just the only thing is that you separated both of them, and then of course there will be linking forces. Here this force is the force that the pendulum is producing on the cart, and this is the force that the cart is producing on the pendulum. By Newton's third law, you know that these two forces are the same in magnitude, but of course that they are directed in opposite directions. And you have something similar here for the force acting in the x direction. So body 1 will just use one variable because it has only 1 degree of freedom, and here we'll put a frame x2 y2 to describe this pendulum, and we'll also of course use the angle that the pendulum makes with the vertical axis. Okay, so the next step is for each body to write down Newton's equations, and I'll try to do this on this slide. So we start with body 1, so mass of cart times x1 double dot is equal sum of the forces. You have F acting, then you have F1 2x, and you have the friction force Cx x1 dot, right? So this is the only equation of interest for body 1, right? Then we have to do the same thing for body 2, but here there is translation and there is rotation, right? We'll do first the two equations in translation. We'll start with the x-axis. So you have the mass of the rod times x2 double dot, and then we have to look at the forces that are acting in the x direction, and I see only one force in the x direction, and it's of course F1 2x. Okay, so this is in the x direction, and I can do something similar for the y direction, sum of the forces, and now I can see two forces. There is this one here, it's acting, you have to in the other direction than y2, so you have to put a minus sign, F1 to y, and then you have gravity which is acting in the direction of y2, so we have plus m rod. Okay, so this is everything that has to do with translation, and now I need to write down the equation for rotation, right? Okay, so I'll write it up here. I have to find some space. So we'll take the moment of inertia and we'll call it GCM for center of mass times the double derivative of phi, and now I have to write the net torque. Okay, so which are the forces which are going to produce a torque? Well, gravity is not going to produce a torque because it's acting at the center of mass, and the whole system here turns around the center of mass, so there will be no contribution of gravity. There will be contribution from these two forces, and of course from this one. The easiest one is maybe to write this torque here, this friction torque. So you have minus C phi times phi dot. Okay, and then you have these contributions here. Okay, I'll have to show you. Okay, and here I have something similar. Okay, so we'll have a contribution of this force, but it has to be projected on this axis here times the length of the rod, and it's positive. No, sorry, it's negative. So it will be minus L rod. Okay, and then it involves the cosine of phi times F1 to x. A good trick to know how it works is to see the situation when phi is equal to 0, and if phi is equal to 0, we have indeed the full force F12x that will producing a torque, okay, and this is indeed what we see. And then we'll have something related to this force here, and it's minus L rod. This time it will be sine phi times F12y. And indeed you see that when phi is equal to 0, there is no torque that is produced, and this is indeed what we've seen. Okay, so now we have written the equations of motion using Newton's second law for each body. So the equations that I had written previously are now shown over here. So one equation in translation for body 1, two equations in translation for body 2, and one equation in rotation. So you have lots of variables here, but of course these variables are not independent, and this is what we'll do in the next step, right? Write the what is called the linking equations. Okay, I've returned to my original drawing of the pendulum on card, and I want to make clear that there are links between x1, x2, y2 and phi. So let me first draw x1. So this is x1. So this will be x2. And this will be y2. And remember that phi is the angle that the pendulum makes with the vertical axis. Okay, so we have x2 is equal to x1 plus this distance here, and of course that's L rod times sine phi. You see that if phi is 0, x1 and x2 are equal, of course, and y2 is equal to L rod cosine phi. These two equations are kind of linking equations. They link to the different variables. Okay, we've seen that x2 and y2 are linked to x1, okay, and phi. And if you look at it, x1 and phi will be the degrees of freedom, right? So if you have a link between these variables, you also have links when you take derivatives, okay? So if you take the derivative on both sides of these two equations, you obtain this thing here, right? There's nothing particular about taking this derivatives, sorry, so I won't go into the details, right? And here again you take derivatives. Don't forget that if you take the derivative of this thing here, it's the derivative of a product, so it will give you two terms, right? But these equations here are linking equations, and they will be used to eliminate variables. So you can see that x2 double dot is a function of x1 double dot phi dot and phi double dot, okay? And you have something similar for y2 double dot. It's a function of. Okay, so now we will be using these linking equations that we have obtained in the previous slide. So this is the first equation that he had written for body 2 in the x direction, and in the previous equation we had this formula for linking x2 to other variables. It involved x1 double dot phi phi dot and phi double dot. So we replace this in here, and this is what we obtain, right? I'm not going to go into the details of the results, but I just want to explain the philosophy, right? So now we have an expression of this linking force that has to be eliminated, and this is the x equation that we had written for body 1, and as you can see, it involved this linking force, and this is what we're doing, right? We're going to eliminate it, and we are going to replace this linking force by this thing here, and then it's just a question of writing it down properly, and instead of using x1, I'm just going to write it as x. It's our degree of freedom, and when you do that, you already have the first equation. Since you have 2 degrees of freedom, I guess you can expect 2 differential equations to describe this mass on pendulum on mass system. Okay, so now we need to find this second differential equation, right? And for that we'll take the second equation that we had written for body 2, and you can rewrite it to make sure that this linking force in the y direction is appearing, right? It's a function of y2 double dot, and we have seen that y2 double dot can be written as a function of phi dot and phi double dot. So we are going to replace y2 double dot, okay, and we obtain this equation, okay? So this is the linking force in the y direction. In the previous slide we had found the linking force in the x direction, right? So we're taking our third equation for body 2, that's the equation in rotation, and we see that it involves the linking forces both in the x direction and in the y direction, and we have to eliminate them. This one is written over there, and this one here, well, you'll get it from the previous slide. We inject this one here, the formula of the previous slide in here, and then it's just a matter of doing a little of calculations, and you obtain the second law that describes this pendulum on card system. So you have 2 coupled differential equations that are describing this pendulum on card system, and you've seen a very systematic way to obtain this system of differential equations. The problem is that, well, if you have problems with lots of bodies, you have lots of linking forces that you have to eliminate, and then can be a little bit tedious. That will be the advantage of the new method that we'll see next, which is the method of Lagrange. We will now illustrate this systematic Newtonian approach using an example of a mass on a wedge, and we'll make the assumption that there is no friction, and this means that all forces are conservative. So the small mass is this one here, yeah, and the big wedge, and with the mass capital M, is this one here. So we know what will be happening, or we can imagine it. Well, this one will slide down, right? And because we have only conservative forces that are acting, we know that the linear momentum is preserved, so we know that this one must go backwards, right? So the tricky point here is that you have one mass, the big mass, going backwards and the small mass going forwards. And if you want to describe that into an inertial frame, it will be kind of tricky because the motion of the small mass will not be a straight line. This is why we're working with this reference frame and this reference frame. This is the reference frame seen by someone that is standing on the wedge, okay? And since this wedge is being accelerated, we are actually working with a non-inertial reference frame, Q2. So we'll have to take into account the fictitious forces that are appearing, right? Okay, let's have a look at our two bodies. I've drawn my, well, at least I've started drawing my one body diagrams, and we'll start looking at the forces that are acting. Okay, in this body I'm only interested in the direction, right, of Q1. So I'm not interested in the orthogonal direction. So this means that I will not draw all forces because they will not have any influence. So of course there is the force that the little mass is exerting on the big mass, and we'll call it R, and it's acting perpendicularly to the wedge. And of course you'll have, by action and reaction, a similar force acting over here, right? There is also gravity, of course, acting, but that will act perpendicularly to Q1, so I will not take it into account, right? So now we are ready to write second law of Newton in the Q1 direction, and it's simply capital M, the mass of the big wedge, times Q1 double dot is equal to, well, you have to have a look at the component in the Q1 direction. It's this one here, and that will be minus R sine theta. This is equation 1. So why is it the sine? Well, we'll see if the angle is 0, that R will be perpendicular to Q1 and there will be no contribution. Indeed, if you put theta equals to 0 in this equation, this is what you obtain. Let's go and have a look at our second one body diagram. I already have drawn the reaction force. Of course, the second force that will be acting over here is, well, gravity, and it will be pointing downwards. And since we are in a non-inertial frame, and we'll make the assumption, and since Q1 is in this direction, that the wedge will be accelerated in this direction, that we need a fictitious force acting in the other direction. So we'll call that one M1 Q1 double dot. Okay, so now we can write two equations. One equation in the direction of Q2, right? So that will be the second equation here. And then there will be an equation in the perpendicular direction. Okay, so perpendicular to Q2, and this will produce my third equation. Okay, so let's have a look at what's happening in the direction of Q2. Well, of course, you have acceleration in this direction. You have M1 Q2 double dot is equal Well, you have R that is not going to give you any contribution because it's perpendicular to Q2, and the other forces are going to give you a contribution. Okay, and this is the contribution in the Q2 direction, and this is the contribution of gravity in the Q2 direction. So this one will have a negative impact and this one a positive impact. So what will we have? mg sine theta, and this one will be minus q1 double dot cosine theta. Okay, so this will be my second equation, right? Again, if you want to know if this is right here, sine, cosine, imagine what is happening when the angle theta is small. So we'll have a look now at what's happening in the perpendicular direction. In the perpendicular direction there is no acceleration, so we can write 0. Mass times no acceleration is 0. Okay, of course there is the contribution of r. Okay, and the other ones will have a negative contribution. This one here, right, that's for this force, and I have to take this component here. And for gravity it's let's change color, it's this thing here. Okay, so this will give us two negative terms. Okay, let's start with the one that is related to this fictitious force. So that's m q1 dot, and it was a cosine here, it will be a sine over here. And then we have something from gravity, mg, we had a sine there, it will be a cosine now. And we arrive at this third equation, right? So now we have obtained three equations, and we can start by eliminating things. Okay, I have rewritten things a little bit so that we have only the equations that we need, and I have noticed I had forgotten the subscript here, q1. So I have written it down. So the next step is to start eliminating the linking forces, and there is one linking force, and it's R. So R is equal to minus m q1 double dot over sine theta. So I'm going to inject it over here in equation 3. This goes to equation 3, and then we'll have minus m q1 dot over sine theta. I will not write it, I will multiply then the rest of the equation by sine theta, is minus m q1 double dot sine theta times sine theta. So I will have a square over here, and this one here I'll take it to the other side, so we can say is mg cos theta sine theta. So I can write this as minus q1 double dot m plus small m sine theta squared is equal to mg cos theta sine theta. And now I have my result, which is minus mg cos theta sine theta over big M plus small m sine theta squared. So this is my result here, and I don't have to forget that this is an x double dot. It's an acceleration, and as I had expected, I have a minus sign. Okay, so the wedge will be going backwards. Okay, so now I can take this result here and inject it in equation 2. Note that in equation 2 I have mass here, I've got it over here, and I've got it over here. Another thing to notice is that here you have j sine theta and here you have j sine theta, right? So we can write q2 double dot is equal to j sine theta, then have 1 plus, there is the m that is coming from here, the other one has disappeared. Okay, there is a cos theta here, so it gives me cos theta squared divided by m plus m sine squared theta. Okay, I can slightly rewrite this. I will put everything under the same denominator, right? So we'll have j sine theta m plus m sine theta square plus cosine theta squared divided by m plus m sine theta squared. Okay, and if there is something that you know from your trigonometrics course, is that this thing here is equal to 1, and we arrive here at the equation for the acceleration q2 double dots. Okay, so I'll rewrite q2 double dots, and this is my equation. And we have found the solution. Okay, first thing that we can do with our solutions, and I've rewritten them there, is to test if they are okay, if they make physical sense, right? So let's see what we expect here if theta is equal to 0. Well, if theta equals to 0, we expect q1 double dot is equal to q dot double dot, q2 double dot is equal to 0. And if theta is equal to pi over 2, then we expect q1 dot double dot, equal to 0, and q2 double dot is equals to j. Okay, so that's the acceleration. And indeed, if we plug in theta equals 0 because of the sine and the sine, you'll have q1 dot double dot and q2 double dots equals to 0 when theta is 0. If theta is pi over 2, okay, because of the sine here it's a 1, and because of the sine here it's a 1, but here we have a cosine, this will produce a 0, and indeed q1 double dot is 0. This will also be a 1. Okay, so you have the total mass divided by the total mass, and what will be remaining is j. So it's always a good idea to check on the physical reality. Okay, so remember that there are no forces applied here in the horizontal direction. So we can write the linear moment conservation, right, in this horizontal direction. And if we do that, we write that m plus, that's the big mass plus the small mass, times q1 dot plus m q2 dot, but then in the direction that is horizontal, so we have to multiply by cosine theta is equal to a constant. This also means that if I take the derivative, q1 double dot plus m q2 cosine theta is equal to 0, and here I have to put a double dot. Okay, so now I can inject my solution. Okay, so I will have minus m times m plus m g sine theta cos theta, right, divided by m plus m sine square theta plus m q2 dot cosine theta. Okay, so this will give you m plus m j sine theta, then cosine theta, this is this one here, divided by m plus m sine squared theta, and this is indeed equal to 0. Okay, so now after having checked that, I can be pretty confident that my solution is correct.